Researchers are interested in answering all types of questions. Is the Earth actually warming up? Is a new teaching technique better than an old one? Does this type of motor use less fuel than the other one? All of these questions can be answered through hypothesis testing. Simply put, hypothesis testing will lead you to answer questions on a population in an objective way following a series of steps. This video will present the traditional method to do a hypothesis test. The first step in hypothesis testing is stating your statistical hypotheses. The first hypothesis you must state is the null hypothesis. This hypothesis states either that a parameter is equal to a specific value or that there is no difference between two parameters. This hypothesis is symbolized by H0. Here's another way to write down a null statistical hypothesis where both means of two distinct populations are equal. The second hypothesis you must state is the alternative hypothesis. This hypothesis states that a parameter is either less than, not equal to, or greater than a specific value, or in other words, that there is a difference between two parameters. The symbol for this hypothesis is H1. Here's another way to write down an alternative hypothesis where the means of two distinct populations are not equal. In this example, the mean of population 1 would be smaller than the mean of population 2. Let's say that you are studying the impact of climate change on the average rainfall in July for your home area. You do not know whether the climate changes will actually create a variation in rainfall, and if it does, whether there will be more rainfall or less rainfall. What you do know is that July has an average precipitation of 20 millimeters. So your null hypothesis would be that climate change makes no difference, so it would be stated like this. The average of precipitation for all of the months of July is 20 millimeters, which will be equal to the average precipitation for a given month of July. Now, because you have no idea if more or less precipitation will occur, your alternative hypothesis would be written like this, where the average of a given July is not equal to 20 millimeters. When you have no idea if more or less precipitation will occur, you will be performing what is called a two-tailed test. We'll talk more about what this implies later. But what if you knew that the precipitations would actually be higher? Your null hypothesis would be the same thing because it always states the absence of difference. Your alternative hypothesis, on the other hand, would actually be this, that the amount of precipitation will be higher than 20. When you know that the calculated or observed value should be higher than the population parameter, you will be performing a right-tailed test. Again, more on implications of this later. How about if you knew that the precipitations will actually be lower? Your null hypothesis would be the same thing because it always states the absence of difference. Your alternative hypothesis, on the other hand, would actually be this, that the amount of precipitation will be lower than 20 millimeters. When you know that the calculated value should be lower than the population parameter, you will be performing a left-tailed test. Again, more on implications of this later. Once we have stated our statistical hypothesis, the next step is to choose an appropriate level of significance. Remember that we have seen before that a value or a sample mean usually differs slightly from the population mean. That's the sampling error. So even if the null hypothesis is true, it's possible that the amount of precipitation for a given July can be different from 20 millimeters. For the sake of example, let's say that July 2012 has had an average of 18 millimeters of precipitation. So there are two possibilities. The first one is that the null hypothesis is actually true and the difference between the values is simply due to chance or natural variations in precipitation. Now, possibility number 2, that the null hypothesis is actually false and the difference is significant and not due to chance. So when the null hypothesis is false, we can also say that the value of 18 millimeters is from a population whose mean is not 20. So the question is, where do we draw the line between chance and significantly different? Before we answer that question, we must see the two types of errors we can do when doing hypothesis testing. Take a look at this table. We can see that there are 4 possible outcomes, 2 of them leading to a correct decision, 2 of them leading to an error. A type 1 error is when you reject the null hypothesis when it is actually true. And a type 2 error is when you do not reject the null hypothesis when it is actually false. The question of whether or not the difference between the value observed or calculated and the population parameter is due to chance or is significant depends on the probability of doing a type 1 error. This probability is known as the level of significance. This is symbolized by alpha. There are 3 levels of significance that have been determined, notably 0.01 or 1%, 0.05 or 5%, or 0.1, 10%. If we were to settle on 10%, we would have a 10% probability of committing a type 1 error if we were to reject a null hypothesis. Another way to see this is to think of the level of significance as being the area under the curve that is too far away from the population parameter to be due to pure chance. For this course, unless it is otherwise stated, we will use a level of significance of 5%. Once you've chosen your level of significance, you must identify a critical value and as such a critical region. The critical value separates the critical region from the non-critical region. The critical region, also known as the rejection region, is the range of values of the test statistic that indicates that there is a significant difference and that the null hypothesis should be rejected. To find the critical value, you must use the appropriate table. For example, if the statistic you are using is the z-score, you must use the z-score table. Let's go back to a rainfall example when we didn't know what type of modification in precipitation climate change would bring. We know that the population mean for precipitation in July is of 20 millimeters. We also know that for a given year, it's more than probable that precipitations will not be perfectly equal to 20 because of normal variations in rainfall. But where do we draw the line? What would be considered a too low or too high precipitation level that could be attributed to climate change? Consider a level of significance of 5%. Because this is a two-tailed test, the area of 5% will be distributed evenly on both tails of the distribution, like so. Assuming you're working with z-scores, your critical values here are the z-scores associated to an area of 0.025 and an area of 0.975. So if the calculated values, so if you've got 18 millimeters, if 18 millimeters falls within one of these 2 orange areas, you would reject the null hypothesis and state that the value you obtained is significantly different from the population mean. We'll do the same thing, but when we know that climate change will bring more precipitation. Again, we know that precipitation naturally varies from year to year, but where do we draw the line on what is a lot more than normal? Consider again level of significance of 5%. Because this is a right-tailed test, the area of 5% will be entirely on the right tail of our distribution. There will be only one critical value, the z-score, again assuming you are working with z-scores, associated to an area of 0.95. So if the calculated value falls outside of the critical region, you would not reject the null hypothesis and state that the difference in value is due to normal variation. The reasoning for a left-tailed test is very similar, the main difference being the location of the critical region, which would be entirely on the left tail of your distribution. The z-score, assuming you are working with z-scores, is associated to an area of 0.05. So if the calculated value falls inside of the critical region, you would reject the null hypothesis and state that the difference in value is not due to normal variations.